Now that you've learned all about those important periodic properties, it's time to get down to business here and talk about bonding. Remember that compounds far more prevalent and numerous in nature than are the individual elements, and hence it must be a pervasive thing that these atoms of different elements get together and form these bonds. What is a bond? Well, obviously, it's an attractive force that glues two or more atoms together. Another way of thinking about it is that this attractive force then would require that energy be put into the bond in order to break it, and that's always true. Bond breaking always requires that energy be put into the system. We'll talk more about those attractive forces as we go through here, but it makes sense that there would be attractive forces between the nucleus of one atom and the electrons of another, and vice versa. And so we're going to be thinking about that attractive force, that electrostatic attractive force. As I've said 1,000 times before, but bonding about lowering that system energy and nature favoring that lowering of system energy. You can think of it in sort of two ways. One, of course, is that the energy of isolated atoms is relatively high and as a result not favored by nature, and when those atoms get together, either as ions or as neutral atoms, the system energy is lowered and that bonding then is favored. Again, 100-some naturally occurring elements, but millions of compounds, suggesting that this process is pervasive. Chemistry is largely about electrons, and here in terms of bonding we're really focusing in on those electrons, and specifically those valence electrons. You remember those valence electrons are those in the outermost energy shell that we counted in the last video, and these are the ones that are going to be interacting with the electrons in an adjoining energy shell from another atom, or perhaps moving. Remember that the other way of thinking about valence was the number of electrons that were gained, lost, or shared when a bond forms. And so I'm going to try and be super careful here as we talk about valence to be clear on what meaning I'm giving it, whether I'm talking about the number of electrons in the outer energy level or the number of electrons that are gained, lost, and shared. Sometimes it's the same, sometimes it's a little different. Remember that gaining and losing electrons causes the formation of ions, cations, positive ions, and anions, and that this gain and loss can ultimately then result in electrostatic force. So let us consider what happens when we have a sodium atom that has, if you look on your periodic table, one valence electron. It is in the 3s shell, and I'm just going to represent it as this dot here for now. And a chlorine atom, chlorine again, period 3. Remember counting valence electrons across, it gives us 7 valence electrons. And I'm establishing a little pattern here in that I'm going to put those 7 valence electrons around chlorine in groups or pairs. Those pairs are, of course, the 2 electrons that fill the sublevel. You could think of these 2 as being in the 3s level, these 2 as being in 3px, these 2 as being in 3py, and this 1 electron alone for now in 3pz. This electron here, of course, as I said, occupying the 3s level. Well, if you remember our trends in electronegativity and electron affinity, you should be able to figure out that chlorine has a much greater desire for an electron than does sodium. And in fact, ionization energy, since it increases across the periodic table, means that the energy required to remove that electron from the sodium atom is not all that great. And the energy lowering that occurs when that electron is added to the chlorine atom is pretty pervasive. And so nature often conspires to remove that electron from sodium and install it in the empty orbital of chlorine, and now we have sodium with a positive charge having lost that electron chlorine with a negative charge having gained that electron. The sodium ion and the chloride ion then have opposite charges, which of course results in an attractive force between those ions. And as those sodium ions and chloride ions come together, a bond is formed. It's a strong bond. Sodium chloride, in fact, perhaps a familiar substance to you, table salt, is a crystalline substance. It's solid at room temperature, and in fact, it has a relatively high melting point in the vicinity of 800 or 900 degrees, I believe, which is a measure of the degree to which those sodium and chloride ions are holding on to each other. High melting points, high boiling points correspond to strong forces holding the substance together. An ionic bond then forms when we have positive and negative ions and that strong electrostatic attractive force between those two. Well, I'll certainly say more about that in a little bit, but let's consider another possibility where we have two atoms that have roughly equal or not all that unequal electronegativities, and you're going to see that electronegativity becomes the thing that determines what kind of bond forms, one based on loss and gain, which was ionic, and one based on sharing, which we call covalent, valence electrons, covalent meaning sharing those valence electrons. Let's consider the situation between hydrogen and chlorine. Hydrogen has 1 valence electron. Chlorine has 7 valence electrons. But hydrogen, even though it is a group 1 element, is a very, very small atom and has a fairly high electronegativity in the vicinity of 2.1, if I haven't mentioned the scale. The scale runs from about 0.5 to 4. Remember, electronegativity is a relative term and does not have any real units. Such that hydrogen is very reluctant to give up that electron. It has a high ionization energy. And so what happens, the way that system energy is lowered in this case, is that the 1s orbital for hydrogen overlaps with its 1 electron, the 3pz orbital for chlorine, and we make what the chemists call a single covalent bond by sharing those 2 electrons. In this sense, hydrogen thinks it has the 2 electrons that are allowed in the first period. Chlorine thinks it has the 8 electrons that are allowed in the second period. Remember our discussion about valence electrons and that stuff. Both of them are happy, if you want to think about it in those terms, but really what's happened here is that the energy of an isolated hydrogen and chlorine atom are much higher than the energy of a covalently bonded hydrogen and chlorine atom. And hence, nature favoring low system energy, this becomes a covalent bond where the valence electrons are shared, and we have a molecule. The word molecule means a covalently bonded substance where we can point to the actual electrons that are being shared and identify with them. Covalent bond, you remember sharing. Ionic bond about transfer, so that both players believe they have the full valence shell in that instance as a result of electron loss and gain. Again, more on that coming up. So it seems obvious that the thing that governs the kind of arrangement that is worked out in terms of those 2 atoms has to be this electronegativity, the ability of an atom to attract electrons to it in a bond. Although this looks complicated, it really isn't. The type of bond that forms, ionic versus covalent, depends on the differences in electronegativity. Remember I said that electronegativity itself varies from about 1.5 to 4, depending upon which elements you throw into the pot. And so it is the difference in electronegativity that determines what type of bond is formed. If there's a large difference in electronegativity between the 2 players, then the element with the highest electronegativity takes possession of the electron. We say the electron is transferred, and the unit charges, plus or minus, get together, and an ionic bond is formed. If, on the other hand, there are small differences in electronegativity between the two species, I'll call them that, players, whatever you call atoms, then obviously neither one of them can strip the electron from the other one, and that small difference in electronegativity then results in the sharing of those valence electrons and the formation of this covalent bond between the two or more species, as we'll see these molecules that form when covalent bonds make form are going to potentially have more than two atoms. There's really no hard and fast rule, but as we go through here and try and calculate some bond types, we use numbers to separate, if you will, the different categories of bonding. Anytime the difference between electronegativity gets up there around 2 or so, then we consider the electron transfer to be essentially complete, and we declare the bond to be ionic, and we expect the properties of ionic substances. More to say about that coming down the road. Anytime the electronegativity difference is less than about 0.3, then we declare the bond to be one of equal sharing, and that equal sharing then is technically called a non-polar covalent bond. Interestingly enough, much of the time, the difference is substantial, but not huge. And what this results in is a very interesting sharing of electrons, where one atom has more of the electrons than the other one. And this becomes what we call a polar covalent bond. And as you're going to see later on down the road, the development of polarity is hugely important in the behavior of compounds and their physical properties. So these three categories then, pure ionic, pure covalent, non-polar, and polar covalent are essentially worked out based on the differences in electronegativity.